say the charge is plus 1, 0, and 1. This is a relative charge compared to other things. The actual charge on this we can measure
Inorganic
and is very, very small. But it is much. So plus 1 and minus 1.
Okay.
The mass of
There's
atoms,
1
neutrons,
hour.
and electrons has been worked out based on carbon 12 as a reference.
Be about here.
Can potentially be dangerous. If we change this, KC is the
Inorganic chemistry. Okay, KC I already did yesterday. So
we use square.
Hold on.
Here to
I already did this yesterday.
Oh,
it's on one.
Add up to the charge on that.
Okay, should be here. Hopefully.
Arranged by atomic.
Okay, so the structure of the periodic table is arranged by increasing atomic number, not by mass. So it's not by mass, it's arranging increasing atomic number.
Periods will run across the periodic table. They will show a repeating trend.
Repeating trend?
This is periodicity. They will have the same number of electron shells.
Oh, wait, what?
But an increasing.
Oh, they're two different things.
A repeating trend. This is periodicity. They will have the same number of electron shells.
Same number of electron shells.
But an increasing number of electrons on the outer shell.
Same number, wait, periodicity, same number of electron shells, increasing number of electrons. Increasing number. So they have the same number of electron. Wait. But. Okay, I'll find it out later.
To help you remember how many electrons go in each shell. For example, in the first period, period 1, there are 2 elements, so there are 2 electrons. In the second period, there are 8 electrons and 8 elements.
Sorry, what? How's a group? Wait.
Increasing number of electrons on the outer shell. The structure
will
also help you remember how many electrons go in each shell. For example, in the first period, period 1, there are 2 elements, so there are 2 electrons.
Wait, so on the first. Wait. 2? Period 2. Okay, wait, my brain is not comprehending this. Let me see again.
Help you remember how many electrons go in each
Okay, that's 1, 2, 3.
In the first period, period 1, there are 2 elements, so there are 2 electrons.
2 electrons.
In the second period, there are 8 electrons and 8 elements. The same in the third period, there are 8 elements in that period and there are 8 electrons in that.
I actually don't understand this. This is actually insane.
Can be divided up into blocks.
S, P,
the S block,
D, and
the
F
D block,
blocks.
the P block, and the F block.
Yay.
Period 3 goes across here on the periodic table.
Okay, period. Well, that was it. S, P, D,
S,
F. The topic is just.
The periodic table can be divided up into blocks. The S block.
Divided.
The D block.
Into blocks.
And the F block.
Yay. Okay. Wait. Okay, so on the left-hand side of the periodic table, we have the beautiful S block. So I'm going to actually highlight this. S. Oh, can't even see it. S. And then we have the middle. That's not P. I always said that was P, but it wasn't P. It's actually D. So I'm gonna highlight this. S, P, D. That's D. And then F is the right hand side of the periodic table. So I'm gonna do it in green. Yay. So that's P, not the middle one. The right hand side is P. And then we've got the bottom bit, which we don't actually really focus on that much, but that is F. Okay, and that's where elements in the periodic table are placed. So, I was going to say something. Oh, yeah. Periodic table is arranged by atomic number. Yes. It's not by mass.
Period 3 goes across here on the periodic table.
Period 3.
This is an example period, and similar trends are seen in other periods. For example, period 2.
Similar trends seen in other periods.
As we move across the group, we're going to see a decrease in atomic radius.
Okay, so as we move along the group, there's a decrease in the what? Atomic radius. Atomic radius. Okay, so as we move along the group, it can be any group, but if you hold on, you go across it to the right, then it decreases, but the number of protons increase. So protons increase. So wait, yeah. Okay. So does the positive charge in the
so does the positive charge in the nucleus.
I think it also means
the outermost electrons inwards.
So wait, does that mean that the attraction increases as you go along the group? I'll ask ChatGPT. I think it is though. Okay, I have a question. Oh, GPT-5. Okay, I have a question. So it says that as we move along the group, the atomic radius decreases, which I understand. Protons also increase. So does that mean that the attraction between the nucleus and the outermost electron, the attraction is greater as you go along the group, since there are more protons and the electron shells stay the same, so therefore there isn't any electron shielding, right? Yeah. Sounds like you're talking about moving across the period in the periodic table, not down a group. Hold on. Okay, I think I've been scammed. It says move along across the group, yeah. I think she got it wrong. The group. Right, period is across, right? And then group is down. So why has she said the group? Wait. Hold on, I actually think there's a mistake in the video.
As we move across the group, we're going to see a decrease in atomic radius.
A decrease in atomic radius. Okay, wait, I need to figure this out because this is driving me crazy. Okay. Across a period, the number of protons increase, number of electrons stay the same, and the attraction, the nuclear attraction, increases. Wow. Nuclear. That didn't even come into my head. It's as we move along the period, not group. Wow. Okay.
As the number of protons
so that's fair enough. Okay. So it's like if you go across the period, protons increase, electron shells that stay the same, so therefore there's no electron shielding. Nuclear attraction also increases. So yeah, we'll just see where it goes.
Positive charge in the nucleus, further attracting the outermost electrons inwards.
Okay, so we have a graph.
If we look at the trends in first ionization energy, there will be a decrease between
1,
magnesium
2,
and
down.
aluminium.
1, 2, 3.
This
Down.
is as the S shell gets full and
That's
starts filling up P
aluminium.
orbitals.
That's
There is
sulfur.
also another drop.
So there's a drop between. Okay, you know what? Let me write them all down. That's Na, Mg, Al, Si, P, phosphorus, sulfur, chlorine, and argon. So it drops between magnesium and aluminium. So magnesium to aluminium, it drops as the S shell gets filled. Okay, wait. This is because the S shell gets filled and then it moves on to the P shell. But I do have a question, because now first ionization isn't about what gets filled first, it's about the amount of energy required to remove an electron from 1 mole of gaseous something. I need to check that again. So why is she talking about the first ionization energy?
Between groups 5
Drops
and
as
6 between phosphor and sulfur as pairing starts.
pairing.
Repulsion increases slightly.
Wait, so from P
Sodium,
to
magnesium,
S
will have strong bonds leading to high
as
melting
pairing
and boiling
stuff.
points. Silicon also has strong covalent
And
bonds. It is a giant structure. It will have high melting and boiling points.
repulsion.
Fluorine, sulfur, and phosphorus
Increases.
are simple covalents, so they will have a weak
Wait, I'm very
intermolecular
confused.
bond.
Okay, I have another question. From Mg, from magnesium to aluminium, it drops because the S shell gets filled and it moves on to the P shell. When it goes from phosphorus to sulfur, it drops as pairing starts and repulsion increases. So what does it mean by the pairing starting and the repulsion increasing? Does that not happen to magnesium and aluminium, or is it just two things that you can say? I hope it's not that confusing. Okay, talking about ionization energy trends. No special phosphorus. We're not pairing up electrons in the same. We're just putting new ones to empty. Okay, I don't really understand. So what does it mean by pairing starts and repulsion increases? Okay, P shell subshell has 3 orbitals. No pairing yet. Oh, okay. You know, this is why I love ChatGPT, because it makes sense. Okay, by pairing, it means from this and then just single to this, and then goes 1, 2. First pairing begins. Yes. Okay, this is great. But to find out, hold on. Okay, so to find out whether the first pairing has begun or not, do you just have to write the SPDF thing, like 1s2, 2s2, 2p6, and that stuff? So yeah, you do that. Okay, I understand it. That's good.
Bonds leading to low boiling points. And argon is monoatomic, very low boiling points. bonds. It is a drying structure. It will have high melting and
Sodium,
boiling points.
magnesium, and
Chlorine,
aluminium
sulfur, and phosphorus are simple
have
covalent, so they will have a weak intermolecular bonds, leading to low boiling points.
So since they have
argon
strong
is
bonds, they've got
mono,
high
very low boiling
melting
points.
point and boiling point.
For group 2, we are looking at the melting and boiling points.
Si, which is
Chlorine,
silicon,
sulfur, and phosphorus are simple
has
covalent, so they will have a
strong
weak intermolecular bonds, leading to low
covalent
boiling
bond.
points. And argon is monoatomic.
It's actually very
low
confusing.
boiling
I need to see how to do this.
And 6, hydrogen phosphorus. So does the positive charge in the nucleus, further attracting the
They look
outermost
from
electrons
inwards. So then, okay, that makes sense.
If
So now
we
we
look at the
have.
trends in first ionization energy, there will be
Okay, this I understand. Is just the next thing that I don't
there is
understand.
also another drop between groups 5 and 6. Sodium, magnesium, and aluminium will have strong bonds, leading to high melting and boiling points.
Okay, and
Silicon
then
also has strong covalent bonds. It is a drying structure. It will have high melting.
so since sodium, magnesium, and aluminium are metals, they have strong bonds. That's why silicon has strong covalent bonds, because it can form covalent structures. I think I'm getting somewhere. I think I'm starting to understand it slightly. It's kind of hurting my brain, but okay, I think I'm getting the idea. So silicon has strong covalent bonds because it's a non-metal, so it can form covalent bonds with metals. So therefore it has a giant structure. Wait. Hold on. Covalent is non-metal with non-metal, not non-metal with metal. That's ionic. Wait, I actually need to find out. Why does silicon have strong covalent bonds? How do you know that it has a covalent bond and not anything else? I'm so confused. I don't know, like, how do you know it's not? Why does it speak in a different language? Can you please say it in English? Okay, that's a bit confusing. Say it in English, please. Okay, finally. Okay, covalent bond is when two atoms share electrons, but those are like non-metal. Okay, but a strong covalent bond means those that are shared electrons, held very tightly. Okay. Pure silicon forms a giant covalent structure. Are you supposed to just know that, or? Silicon is a non-metal, tends to form covalent bonds, not ionic ones. Okay. Structure, giant covalent lattice, high melting point. Okay. So is it just something that you're supposed to know, or do you have to learn it? So does that mean that all non-metals form covalent bonds? We're going to see. Why is it? I just don't understand. Alright, okay. You don't have to guess blindly, but in exams you often need to already know which substances. Okay, great. Metals are non-metals, usually ionic. Non-metal, non-metal, covalent, metal, metal, metallic, obviously. Okay. No, not all non-metals form covalent bonds. Okay, I think I just have to learn it. Okay, so now we know that silicon has strong covalent bonds. It forms a giant structure.
Melting and boiling points.
High melting.
Chlorine, sulfur, and phosphorus are simple covalent, so they will have a weak intermolecular bonds, leading to low boiling points.
Cl2.
And argon is monoatomic, very
S8.
simple covalent, so they will have a weak Magnesium and aluminium will have strong bonds, leading to high melting and boiling points.
Then there's silicon, which has strong
Silicon also
covalent
has
bonds.
strong covalent bonds. It is a drying structure. It will have
High melting point and boiling point.
Chlorine, sulfur, and phosphorus are simple covalent, so they will have a weak
Simple
intermolecular
covalent.
bonds leading to low boiling points. And argon is monoatomic, very low boiling
They have weak
For group 2, we are looking
intermolecular.
at the ones going down on the left-hand
Okay, now
side.
do you say intermolecular
And
forces
argon
or
is
bonds?
monoatomic, very
Weak
low boiling
intermolecular. Okay.
point. So they will have a weak intermolecular bonds leading to
Bonds.
low boiling points. And argon is monoatomic, very low boiling points.
Argon is monoatomic,
For group 2, we are
which
looking at the
means
ones
that it
going
has
down on the
very
left-hand side.
low melting
These are
point.
the alkaline earth metals, and
and
they would have
boiling
2 electrons in their outer shells.
Now we're on
This
group
makes them
2.
all very reactive. As you go down the group, the atomic radius increases. This is due to the increase in the number of electron shells.
Okay. Group 2.
These are the alkaline earth metals, and they would have 2
Alkaline.
electrons in their outer shells. This makes them all very reactive. As
They
you go
have
down the group, the atomic radius,
2.
the melting point will
So it makes it
decrease.
very
This is due
reactive.
to the increased distance between the nucleus and the outermost electrons. This makes them all very reactive. As you go down the group, the atomic radius increases.
Okay.
This is due to the increase in the number of electron shells. The melting point will decrease. This is due to the increased distance between the nucleus and the outermost electrons, reducing the electrostatic attractions between atoms. There is a decrease
Atomic
in
radius
the first
increases
ionization
down
energy. As the number of shells increases, the
the group.
shielding increases. Reactivity increases as you move down the group, as outermost electrons are more easily lost.
Increased distance between
If we have
nucleus
group 2
and outer
metal and water, we will get a group 2 metal
Okay,
hydroxide and
melting
hydrogen.
point
A group 2 metal plus oxygen will give us a metal
decreases.
oxide.
Can actually talk so fast? Hold on.
The melting point will decrease. This is due to the increased distance between the nucleus and the outermost electrons.
Okay, that's because of an increased distance. Increased distance between nucleus and outermost electrons. So therefore the attraction isn't very strong anymore, so melting point decreases because then it needs less what's the word? Less energy to overcome the bond.
Reducing the electrostatic attractions between atoms.
Reducing.
There is a decrease in the first ionization energy. As the number of shells increases, the shielding increases. Reactivity increases as you move down the group, as outermost electrons and more ionization energy. As the number of shells increases, the shielding increases.
Okay, if shell number increases, then so does electron shield.
Reactivity increases as you move down the group, as outermost electrons.
Reactivity increases as you go down, and that's because the outermost. That's because the outermost electrons are more easily lost.
Electrons are more easily lost. If we have a group 2 metal and water, we will get a group 2 metal hydroxide and hydrogen. a group 2 metal plus.
Oh no, I really don't like doing this. Group 2 metal. So if you add a group 2 metal, add water, and then we've got group 2 metal, add oxygen. The first one, if you add water, makes the metal hydroxide. Add hydrogen. That's fine, I understand that. Then it makes metal oxide, I guess, just with oxygen.
Metal oxide. Group 2 hydroxides become more soluble as we go down the group. Magnesium hydroxide is very sparingly soluble, almost insoluble, and it's used to treat stomach acid. Calcium hydroxide is used. Magnesium hydroxide is very sparingly soluble, almost insoluble, and it's used to treat stomach acid. Calcium hydroxide is used to neutralize acidic soils. Calcium oxide.
Wait. Magnesium oxide is sparingly soluble and it's used to treat stomach acid. Then there's calcium oxide. Is used to neutralize acidic soils. It's used to neutralize acidic soils. Then we have, oh wow, what's this?
Treat stomach acid.
Calcium oxide.
Calcium hydroxide is used
hydroxide.
to neutralize acidic soils.
So that's hydroxide. Why is the other one oxide then?
Insoluble.
Is that, or did I hear it wrong?
Group 2 hydroxides become more soluble as we go down the group.
Oh yeah, okay.
Magnesium hydroxide is very sparingly soluble, almost insoluble, and it's used to treat stomach acid. Calcium hydroxide is used to neutralize acidic soils. Calcium oxide and calcium carbonate is used to remove sulfur dioxide from flue gases. Magnesium can be used to extract titanium. Carbonate is used to remove sulfur dioxide from flue gases. Magnesium can be used to extract titanium. Titanium needs to be very pure, so it can't be extracted just by carbon. It is a batch process, making it very expensive. It also uses large amounts of electricity.
Am I supposed to remember that equation? In A-level AQA, magnesium, we learned that magnesium is used to extract titanium. Are we supposed to learn the equation? Is it like in the spec? Because I do not remember. Well, this is taking a while. Okay.